So the random variable is the variable whose value is determined by the outcomes that are possible in the probability experiment. So if we're talking about creating a probability distribution and looking at random variables for rolling a die, this first line with the x's, these are your random variables. And I'm just going to put RVs next to it, but if you need to write out the words random variables so you know what that means later, please do that. So those numbers are the outcomes that are generated by the experiment. You don't know which ones you're going to get until you roll the die. It's random. Does that make sense? Okay, random variables represent the outcomes in the probability experiment. In the probability distribution, you label the probabilities for each random variable. So we see the P of X, these are just probabilities of your random variables. Okay, so P of X is the probability of each RV. Now, some probability distributions have special names. This is one of them. Because your probabilities are all the same, this is called a uniform distribution. Now, not every probability distribution is uniform. Only those that have the same probability for every single random variable. Okay, so this is a special one. And one thing that you can do is check your probability distribution. If you add up all these probabilities, 1, 6 plus 1, 6 plus 1, 6, and you got 6 of them, right? You get 1. So we know we have all the possible outcomes, all the random variables are accounted for, and their probabilities are good because we add up to 1. If you create a probability distribution and then you check your probabilities, they don't add up to 1, you likely are missing an outcome or you have miscalculated probability for some of your outcomes. Now, if we're doing any rounding as we're calculating probabilities, you might be really close to 1 but slightly off because of rounding. So that could probably be okay, but you also want to just double check that you calculated things correctly. Okay, now we're going to do an example for a probability distribution that is not uniform. We're going to spin that spinner that you see on your paper. And do you see that the spinner is divided into 3 equal parts? Okay, we're going to let X be a random variable that represents the sum when the spinner is spun twice. So our random variables are this top column. I'm going to let you do the probabilities here in just a little bit. But in the second one, that outcome should, I suppose, be really listed as the number of outcomes. Okay. If we want our sum to be 0 and we're spinning the spinner twice, what numbers could I land on to get a sum of 0? 0 and 0. So there is one outcome. If I were trying to spin the spinner twice and get an outcome of 1, how many ways can I do that? 2. I could get a 0 and a 1 or a 1 and a 0. Okay, so there's 2 outcomes there. What about getting a sum of 2? 1, 1.
2, 0.
0, 2, 2, 0.
Actually,
1, 1 is the same, right? So there's 3. Okay, and then here we would have 1 and 2, 2 and 1, and then just 2 and 2. Okay. So you just have to think about all the different ways that you can get that sum. Okay, so what's the probability of spinning a 0? 1/3. And then spinning another 0? 1/3. And what should you do with those 2 probabilities? multiply them. I'm getting a 0 and then another 0, and then means multiply. So the probability of a sum of 0 is 1/9. Okay, talk with your pods and see if you can come to agreement on your other probabilities.
I know the 4 is right.
For the next one.
And then
That's added. So let's go find out.
so there's
If you want me to find out. Okay, what do you think?
I think so it's 1/3 plus
It'll be 1 less. Oh, yeah.
maybe because it's just like a number of ways over 9.
Yeah,
Isn't that how it is?
Yeah.
Do you want us to simplify it?
Yes.
I'm still.
We have to-
Okay, so as I'm walking around, I'm seeing really good work. You'll have to remember, like, there are 2 possible outcomes here, getting a 1 and a 0, or a 0 and a 1. So each of those individually have a probability of 1/9, but because there's 2 ways to do it, we would add those together, so I could get 1, 0, or 0, 1, 1/9 plus 1/9. Okay. And then we'll have 3/9, which is 1/3, 2/9, and 1/9. Now, this one is no longer a uniform distribution because the probabilities aren't the same. But we can describe this distribution as symmetric because you may notice it's the same on both sides. It mirrors itself. So you can have symmetric distributions and non-symmetric distributions. We need to draw a histogram. That's in the directions up above. Okay, so it says, and draw a histogram. And what I would say about a histogram is it's basically a bar graph with no spaces. So in a bar graph, you separate the bars. In a histogram, they build like right next to each other. There's no space in between them. So let's, in this space below, create a histogram. Now, your horizontal axis is going to be your random variables, which are your sums. So we know spinning this spinner twice, the only sums that are possible are 0, 1, 2, 3, and 4. The vertical axis is going to be the probabilities. Now, all of those probabilities should have added to 1, which they did. 1/9 plus 2/9 plus 3/9 plus 2/9 plus 1/9. But what is the highest probability? The 1/3 or the 3/9? So I always look at my probability distribution and I just say what is the highest probability? 3/9 or 1/3? So that's as high as I need to go in my histogram. So I'm probably just going to break it up. I'm going to have a 1/9. 2/9, and a 3/9 or a 1/3, I suppose I should write, Write it in simplified form. 2/9, 1/3. So these are our probabilities. Okay. And then you just draw the bars. So for 0, we had 1/9. For 1, we go up to 2/9. 2 is 3/9, back to 2/9, back to 1/9. And now you can see also the symmetry, right? There's a middle line there and it's the same on both sides. Are you okay with this? Okay. If you were asked to find the probability in letter B about the sum of at least 3, how can you get sums of at least 3? What outcomes are acceptable?
1 and 2?
Yes, on the spinner, spinning a 1 and then a 2, but in terms of the sums, which sums are at least 3? 3 and 4, right? So to have a sum of at least 3 means my sum is 3 or 4. Keyword or, so I should do what with those two probabilities? Add them. So this one was 2/9, this one was 1/9. That's 3/9 or 1/3. You could use your chart or your histogram to do that. What's the most likely sum? 2. How can you tell it's 2?
It's the highest probability.
It's the highest probability, or in your picture, it's the highest bar, right? Just like visually, it's the highest one, so it's the most probable. Highest bar will be the most probable outcome. Okay, so 2, okay, has the highest probability, which means it has the highest bar. Okay. Okay, so far, anything you want to ask me about? That's a very, shallow look at distributions, okay, how they all work. If you take a probability and stats class, you would go much more in depth. You'd spend a lot more time building distributions, but now you get the basic gist of what's happening, okay? Okay, so flip it over on the back side. We're going to talk about a special distribution that is not uniform. It's called binomial. If you were to take a probability and stats class, you're going to learn way more than uniform and binomial distributions. There's a whole bunch of them out there. Okay, one type of probability distribution is called the binomial distribution. It's called the binomial distribution because it shows the probabilities for a binomial experiment. We don't know what a binomial experiment is, so we're going to describe the characteristics of a binomial experiment below. A binomial experiment will meet the following conditions. You will have n independent trials. The trials are independent of each other. One does not affect the outcome of another. Each trial has only 2 possible outcomes, success or failure. You can also think about that as those things are just complements of each other. So success might be the probability of event A, therefore failure is the probability of not event A. Now the weird thing when you get into the study of statistics, if you're interested in actuarial science, where you calculate risk for different events, and that creates how much you pay for insurance premiums and all that stuff, you're going to be dealing with a lot of things about death, destruction, sad things, right? So you might be interested in what's the probability that a person who smokes cigarettes develops lung cancer, and therefore in the binomial experiment the mathematician would call developing lung cancer a success, and not developing lung cancer would be a failure because we're concerned about that probability. Does that make sense? Mathematicians have no feelings attached to that. Okay, so
Facts don't care about your feelings.
don't let it get mixed up in feelings. I could do an example less death and destruction more related to high school, and just say I want to pick a sample of students and I want to study does their attendance affect suspension rates, and so I just pick random students and I look at whether they've been suspended or not, and I might call a suspension a success and a not suspension a failure, but that's just because I'm just labeling it for the purposes of my mathematics. Okay? So they don't mean good or bad. They just mean it happens or it didn't happen. All right, and then the last one there is the probability of success will remain the same for every trial. And we're going to call that probability P, little p. Therefore, the probability of failure is just the complement of little p, 1 minus p. Since there's only two outcomes, success and failure, it does happen, it doesn't happen. They have to add to 1. So I'll be using my complement. Now, in my formula, you're going to see a 1 minus p in the formula. When I do my actual problems, I just figure out in my head what my 1 minus p is, and I just write down that new probability. I don't actually write out 1 minus p in my work. So you'll see that when I do an example. Here's the formula. Now, if you are taking a probability and stats course, you might be asked to memorize this formula. I will not ask you to memorize it for your test on Friday, but I do need you to be able to use the formula. So that is your main goal for today and tomorrow. Provided the formula, can you do these distributions and probabilities? And the answer should be yes.
Are those P's lowercase?
Yep. Okay, so there's a few things I'm going to point out and name and point to here in the formula. So remember that it's a binomial experiment if you have n independent trials. So notice in this combination right here, your total trials is the first number. Okay, so that n is the number of total trials. That could be the number of packages of strawberries I'm serving from the grocery store. That could be the number of students I select from the student population for my study. It's just however many trials I have. K is the number of successes. And we see K a couple of times right here at the beginning, right? And then we also see K back here, but it's with N. If you have N trials and you subtract K successes, what's left over?
Failures.
The failures. So N minus K is the number of failures. Which the number of failures and the number of successes add to your total. And then the only thing left that we have are the P's and the 1 minus P. Remember, P is the probability of success. So you do your total trials, choose your successes, and then you take your probability of success and you raise it to the number of successes. And then you do 1 minus P, which is the probability of failure. And you raise it to the number of failures. How many times did it fail? So it's probability of success, raised to number of successes. Probability of failure, raised to number of failures. And then you got that combination in the front. That's the breakdown of that formula. It looks a lot worse than it really is. And when I'm doing my actual plugging in, you're going to see my examples. I'm not going to nitpick every single one of those. 1 minus P, I'm just going to do that in my head. If the probability of success is 80%, 0.8, then the probability of failure is 0.2. Don't need to write 1 minus 0.8. Okay. If I have 10 trials and I have 7 successes, then I have 3 failures. I don't have to write out 10 minus 3. 7. let's do an example. We're gonna find a probability of rolling a 5 on a 6-sided die, we'll say, exactly 3 times out of 10. Okay, so I want the probability of 3 successes, which my successes are rolling a 5 3 times. So that's my K. Out of 10 trials, so there's my N. And what's the probability of success? Rolling a 5. 1 out of 6 on a die. Therefore, what's 1 minus P, the probability of failure? 5/6. And I can plug that in. It's a combination of 10 choose 3, because I want exactly 3 successes. Now take my probability of success, which is only 1/6, raised to the 3rd, because I'm going to have 3 of them. And I'm not going to write 1 minus 1/6, although I could. I'm just doing that in my head. The probability of failure is 5/6. If I had 10 trials and I have 3 successes, I have how many failures in the back? 7. The weird thing about this is it's not like exactly like binomial expansion because these things don't match on the back and the pick. Okay, so just be careful there. But I just grouped them. This is all about successes, and this is all about failures right here. Type it in your calculators. You don't need to type each individual piece, just type it all in from left to right. I think this is my answer, so see if you can get that. Type it in a calculator. Try it now. I'm not going to help you on any quiz or test, so you better be typing into your calculator with your little fingers. Get some muscle memory. I gotta talk like that because I get a bunch of people who just stare at the wall during this time. Quinn did a celebration dance.
I did.
So she's ready to help anyone who's struggling. Let us know. Talk to your pod members. Talk to me if you're not getting the correct answer. You know how to go back up and see what you typed in? And then see if you can find your mistake? Okay, so our probability of rolling 3 5s out of 10 is 0.15, or 15%.
1 divided by 6?
I would switch to this one. See what you can do. I'll show you real quick where the combination is. It'll be really nice because you'll be able to track stuff. So first you have to type in the 10.
So Wednesday.
And then you just hit this PRB right there. And then you'll scroll to whatever you want. So you want in CR. Down at the bottom equals. And then you can type in the 3.
That's so dumb.
And now you could do like parentheses, 1/6 to the 3rd.
Because they said that if they were to add extra minutes,
1 divided by 6. Close your parentheses. And the exponent is this thing that looks like an up arrow. No, you just hit it. And then raise it to the 3rd. So it's saying like up to the 3rd. With parentheses. Did you get it, Lexi?
Yeah, but
Logan, did yours work? Okay. Okay, now we're going to do the bigger problem. According to a survey, listen, 62% of adults have visited the dentist in the past year. You ask 5 randomly selected adults whether they have had a dentist visit in the past year. Draw a histogram and a binomial distribution for your survey. So I guess you have to think about, like, what are we investigating? Have you gone to the dentist? So let's call success, I went to the dentist. Failure, I didn't go to the dentist. So we can say success equals dentist visit. Failure equals no dentist visit. Now you don't always have to write those things down, but in terms of purposes for our notes, that might be helpful. Okay, now we need to try to pick out all the numbers that we're going to be using in that formula. So one of the numbers we need is n, our total trials. Anybody think they can find the total trials in that problem? 5. Yeah, we're randomly selecting 5 people to ask if they've gone to the dentist or not. So our n is 5. We said our probability of success was visiting the dentist. So what's our probability of success? Yeah. 62%. In order to use that in the formula, we're going to have to change it to a decimal, 0.62. You could change it to a fraction if you wanted to. And if my probability of success is 0.62, what's my probability of failure? 0.38. Okay. Now, on this problem, this is a long problem, you guys. And the reason why it's long is, unlike the last example, it doesn't tell me how many successes. And I want to create a whole probability distribution and a histogram. So that means I need all the successes that are possible. So if I survey 5 people, how many of them could have gone to the dentist? 5 or 4 or 0 or 3 or 2 or 1. So I gotta have all those probabilities. I usually start at the lowest probability, which Katie said was 0. Okay, it's a probability of 0, probability of 1, probability of 2, probability of 3, probability of 4, and finally we're going to do a probability of 5. Now, I'll write out the first 2, but once I get the first 2, it's all just like a pattern, right? I'm just going to do my calculations in my calculator. So, for the probability of 0, I would do my total trials Lexi gave us was 5, choose 0, because we're going to have no successes. Nobody went to the dentist. Our probability of success is 0.62. We're going to raise it to the 0. And our probability of failure is 0.38. Charlie, you can put that in the recycle bin for me. It's distracting me. 0.38 raised to 5th. Now, before I get to my calculator, I'm going to set up the next one, right? If I have 1 success, my 0 changes to a 1, and my 5 failures change to 4. So what I want you to do is type in the first one. I'll put up my decimal answer so you can see if you get the same thing. And then you guys have those calculators where you can just hit up, go back into your work, and if you want, you can just change the numbers that you need to change. That way you don't have to keep typing in combinations. If you want to, you can, but you open yourself up to more keystroke mistakes. So I'll put up my answers and then come walk around. Let's see. Let me know if your numbers don't agree with either of the 2 on the board, the first 2. Oh, and I'm going to by on other people's answers. And the next one, that was 2, right? The one on your calculator.
Yeah.
Steal your answer. Okay, so that's just scientific notation, which you would just move it over to the left. But if you do shift, setup, if you go to fix, it's saying like, do you want to do like how many decimals after the decimal? Like how many numbers after the decimal? So if you max it out at 9, it'll give you 9 numbers after decimal. So if you want to change that, you can always go back into that mode. But it should leave it like that. I don't know if it's true after you shut it off. Okay, so the formula looks really terrible, the work looks really terrible, but it's really just calculating the same thing, changing a few numbers, the number of successes and the number of failures. Does that work okay for you always? So if you have your probabilities, then you can make a distribution for your survey. I think I'm a little low on space, so let me see if I can move this so I could get some more space. Oops. Okay, so I'm going to build a histogram. And my outcomes were people who went to the dentist 0, 1, 2, 3, 4, or 5. Remember, you don't always have to go all the way up to 1 on probability because your highest probability may not be 1, even though these numbers should add to 1 or close to 1 because we rounded. So my highest probability is when I have, 3 people who visit the dentist, 0.34. So then I might choose to go by like 0.1s. Because then I'll hit all the probabilities within that range. Now, something like that first probability, 0.008, that's really small. That's like 0.8%, not even 1%. So when I draw that, I'm going to draw it really close to the bottom. And 0.064, that's about a little over halfway to 0.1, but I'm not even to a 10th, right? Okay, so I'm going to go up. And then finally I could go 0.21, 0.34, 0.28, and 0.9 is just under, 0.09 is just under 0.1. I'm not really too picky about like the exactness of the height of your bars, right? It's just like they should be in the right area. They should, like the middle one should be the tallest. The fourth one from the left should be the second tallest. The one on the left should be the smallest. Okay, Sierra.
I noticed like there was like a pattern in like the 5 pick 0.
Yes?
Or like the fact it's 0 and then like the first superscript is also 0. Like
5 choose 0.
the 0 in the combination thing and then the 0 in the
Exponent?
yeah,
Yes.
they're always like those two spots are always the same.
Yes. In the formula, those are both K's, right? Number of successes. So that should always be true. Yes. Good. You can use that pattern. And that they always add, the other two add to the total trials? Yes. Okay, any questions about what we got up there? Okay, can you answer the last couple questions? What's the most likely outcome?
3.
3 people go to the dentist. Some people are scared of the dentist. What's the probability that more than 3 people surveyed have visited a dentist in the past year?
I thought 0 equals 0 2 by 2.
Well, so I'm going to write it out with probability notation. Probability more than 3. What kinds of outcomes when you survey your people are more than 3?
4 and 5.
4 or 5, right? More than 3 people would be 4 people or 5 people. So you just go up to your probability distribution or your histogram and add up those numbers, right? Is that what you did, Lexi? Oh, okay. Add them. Because it's 4 or 5, and or means add. So 0.28 plus 0.09. Is that 0.37?
Yep.
So you just have to figure out like which of those bars are acceptable and then add up those probabilities at the end. Now there's a few problems for you to try tonight. And tomorrow we'll begin class with probably our concept check over 10.4 to 10.5. So that's or add and subtract probabilities, 10.4. Permutations and combinations, there's not going to be binomial expansion on it. And then you'll have a work day for another practice with binomial experiments. And I'll also give you your chapter 10 test review because your test is on Friday.
Yeah, pass the